All right, we're back. We're back. Welcome back, everybody. Today, we're going to talk about rational functions, more specifically, the local behavior of rational functions. One of the things that I like to do with this course is split up our exploration of rational functions between what happens locally, like at the holes, the intercepts, the asymptotes, and then what happens globally, like the end behavior. That's the basic idea, okay? Let me pull up the slides and we'll get started. Here we go. Last two sections of this chapter. So here's the overview. We're going to get some motivation for what these things are, why we care about them. We'll get a definition of a rational function. We'll talk about the domain of a rational function. Then we're going to talk about local behavior, starting with the zeros of a rational function. We're going to review a couple important graphs that you should have memorized. We're going to take a look at the limit operator again and expand its abilities just a tiny bit. Then we're going to talk about vertical asymptotes and holes of rational functions, and then finish up with some helpful Mathematica commands because, again, Mathematica can help. Well, yeah, we'll get to that. All right, so in the previous sections, we very thoroughly studied polynomials and how their zeros are intimately connected to their factors, right? We drew the analogy between integers and polynomials via the fundamental theorem of algebra and the fundamental theorem of arithmetic. We deployed the polynomial division algorithm to generalize the process of factoring to polynomials, and we explored how the remainder completely determined whether a divisor was a factor or not, right? 1 second here. What's going on there? Okay. So now we're going to explore what happens when you divide two polynomials, and we're going to draw the analogy between rational numbers and rational functions. So that's the next couple sections here, okay? So first we need a definition. What is a rational function? A rational function is a function of the form R of x equals P of x over Q of x, where P and Q are polynomials. So we are literally talking about a ratio of polynomials. The domain of a real valued rational function is all real numbers where the denominator is not equal to zero. One thing that I'll give a little heads up here, we're not going to be including imaginary numbers in our exploration of rational functions, even though they could be. So we're going to restrict ourselves to purely real numbers when we talk about rational functions, okay? So you don't have to worry about the imaginary unit. You don't have to worry about the complex plane. But again, always have an eye toward generalization. All this stuff can be generalized to include complex numbers, okay? All right. So if P and Q, if these two polynomials, if they don't share any common factors, then we say the rational function is in lowest terms. Just like when you're working with rational numbers, right? If they don't share any common factors, a lot of times your teachers will say, oh, it's in lowest terms. For example, 1/2 is in lowest terms, but if you compare it to 2/4, 2/4 is not in lowest terms because the numerator and the denominator share common factors, right? So 1/2 is equal to 2/4, but this is in lowest terms. This is not in lowest terms. Sorry, bad handwriting. Um, Yeah, so if there are no common factors, we say in lowest terms. Now, when the denominator is equal to zero, one of two things will happen. There will either be a vertical asymptote there, or there will be a hole in the graph. We'll talk about those today. The value that makes this zero is only going to give a hole if there's an equivalent canceling factor in the numerator, kind of like this situation here. You're only going to get a hole when you've got equivalent factors in the numerator that would cancel each other out. And what's really cool is the hole will occur exactly at the point given by the simplified or reduced rational function, the function that's in lowest terms. So if you want to locate the location of the hole, reduce the fraction and then plug in where that hole, the x value where that hole is, and it'll give you the y value. We'll see that in just a few minutes here. First, I want to do this though. So this is an example I want you to try at home. Get those juices flowing early on here. I want you to try to find the domains in R. We're only working over R here of the following rational functions, right? So think about it for a minute. Okay. Now, as always, verbalize something. Give your brain that feedback. If maybe what are you going to do first, or if you're finding the domain of a rational function, what do you need to check? All right. And now work it out on your own, and we'll do it together in just a minute. Hey. Okay. So remember, the domain of a rational function is everywhere where the denominator is not zero. And we got some practice with that back in chapter 2. Now we're going to leverage it again. It's the same process, nothing really new to learn here. So what's the domain of this function? As long as x is not -5, we're good. What's the domain of this function? Well, the denominator is a difference of squares. The denominator is x squared minus 9, which is x minus 3 times x plus 3. So the domain of this is everything except plus or minus 3. Here, the denominator is t squared plus 1, and since we're working over r, we can't factor that any further. That's fully factored. So here's a rational function where the denominator is never equal to 0. So the domain is all real numbers. Yeah, here's a rational function where the domain is all real numbers. Now, here's one that's interesting. Actually, let me pull these up so you can take a look. This is what I was saying before. Here's one where you could factor the numerator. Or I'm sorry. Actually, this one's just going to be x is not 4. Yeah, that's it. That's it. Okay, next one. Oh, yeah. Okay. So zeros. Yeah. So now we're going to talk about the local behavior, zeros of a rational function. So if you're given a rational function in lowest terms, the zeros of the rational function itself are the zeros of the numerator, p of x. Here is the proof. It's a very quick and easy proof. If you want to know the zeros of your rational function, and your rational function is written like this in lowest terms, multiply both sides by q of x, and you get p of x equals 0. So when we talk about the zeros of a rational function, we're really just looking at the numerator as long as the function's in lowest terms, all right? Looking at the numerator. Okay, so since the zeros of a rational function are just those of the polynomial that comprises the numerator, finding the zeros of of a rational function is equivalent to finding the zeros of a polynomial, which we now know how to do very well from the previous sections. All that buildup about polynomials, right? Finding the zeros, factoring, the division algorithm, all that stuff. We can leverage all of that to find the zeros of a rational function. We just focus on the numerator and then find the zeros of the numerator. That's it. Moreover, this is one thing I think is pretty cool. The local behavior of the graph at those zeros follows the same guidelines that we saw for polynomials before. Maybe you kind of remember it. Maybe you kind of remember it. The proposition is almost a copy paste of what we saw when we were studying polynomials. But let's say you've got a rational function in lowest terms. Suppose that r is a zero of the numerator. If the multiplicity of r is even, then the sign of r of x will be the same on either side of r. And if the multiplicity is odd, the sign will be different on each side of r. It will change. So maybe this big idea sounds familiar. In other words, if the multiplicity of a zero is even, it'll look like x squared or negative x squared there. And if the multiplicity is odd, then it will look like either x, negative x, or x cubed, negative x cubed, like so. So that stuff that we learned about polynomials, all of it is just coming in to help us easily study rational functions. That's pretty much it. If you've got a zero of a rational function and you want to know what the graph looks like when you're at that zero, look at the polynomial and is the multiplicity even or is it odd? And that'll tell you all you need to know. Remember, I'm saying look like in quotes here. This is very hand wavy. It's not that it's going to be exactly x squared or exactly x or whatever, but it's going to look kind of like that. It might be a little flatter, but it's going to do that. That's the basic idea. Okay. Just give you some intuition for it. Okay. Now just want to refresh your memory about some important graphs that you should have memorized. You needed to memorize these back in chapter 2. If you haven't, do it now because you're going to need them. And now we're going to see why we needed them. All right. So first, the graph of 1 over x, this one. We've been looking at 1 over x since day one, pretty much, right? Lesson number one. That's 1 over x. And then 1 over x squared looks like this. So we're going to need to know what those graphs are because they're going to help us characterize the asymptotes of a rational function. All right. But before we can talk about asymptotes, we need to revisit the limit operator. So let's talk again about the limit operator. Remember, the limit operator looks like this. And previously, when we were exploring the end behavior of polynomials, we were talking about what the end behavior looked like for a polynomial. And we were like, okay, well, what is the limit as x goes to infinity? Is it plus or minus infinity? What is the limit as x goes to negative infinity? Is it plus or minus infinity? Well, we can also use the limit operator to analyze the behavior of a function as it approaches a point, as the graph approaches a point, right? So here is what we call an infinite limit at a point. So let's say we have a function that's defined on both sides of a number a, but maybe not at a itself. Then we would say that the limit as x approaches a of f of x is positive infinity if the values of f of x get arbitrarily large the closer the values of x get to a. Okay. We're not talking about equal. We're not talking about getting at a. That's one of the beauties of working with the limit operator. We're not just plugging in the point. We're talking about where the function's going as we get close to that point. Not at the point, but just getting close to the point from either side. So here's a good picture of that. This is the number a. Actually, let me do this. Say that's the number a. And what we want to look at is the behavior of f of x as x approaches a from the left and from the right. And here you can see that what's happening is the function is actually blowing up to positive infinity when you approach from both sides. So as x approaches a from the left, the function blows up to infinity, the value, the output of the function, right? And then as x approaches a from the right, the output values also blow up to infinity. So we're just saying, hey, the limit as x approaches a is plus infinity. That's it. So now we're approaching a point instead of approaching plus or minus infinity. That's it. Okay. Now is the time when I'll mention this notational note. I think I mentioned it before, maybe I mentioned it in class, but a lot of times, just because things get very cluttered, we will omit the brackets or the parentheses here, and we'll often just write limit as x approaches a of f of x. Just a reminder, there's no multiplication going on or anything like that. This is just limit notation. I'm sorry, this is just function notation. Remember, the limit operator is a function. We're putting f of x into that function, and it's giving us a result. So this is really just kind of a simplified version of the notation, just to make it a little less cluttered, okay? Just to save a little bit of clutter. So if you see this, it means this. That's all I'm saying. Okay. We can also talk about an infinite limit that is negative as you approach a point. So here, as x approaches a from the left and the right, f of x plummets down to negative infinity. So we write that the limit as x approaches a of f of x is negative infinity in this case. The function values are going down just like that, right? That's what it means. So this means this, okay? But one thing I got to point out here is the behavior as we approach a point may not always be the same from the left and the right. So we need a way to specify that. Here, when we just say that the limit as x approaches a is something, we're saying from both sides, from the left and from the right. But we can split that up into two possibilities. And so we have these things called left-handed limits and right-handed limits, and they are exactly what you would think, approaching from the left or approaching from the right. So we use this notation. I'm going to zoom in on it. We use this notation, a little superscript negative sign, to indicate that we're approaching from the left, from the negative direction, okay? From the negative direction. And we can say things like, oh, the limit as x approaches a from the left of f of x is plus or minus infinity. So here's an example of a function right here, where as x approaches a from the left, f of x approaches negative infinity, just like that. So the limit is negative infinity. But notice that's not the same if we come from the right. So if x approaches a from the right, well, f of x is just approaching that hole right there, not going to plus infinity or minus infinity. This is why we need to be able to talk about like left versus right. So here, as x approaches a from the left, the function goes to negative infinity. But as x approaches a from the right, it goes to whatever this number is right here. I don't know what it is. Doesn't really matter in this context, but so that's what we call a left-handed limit. And again, the notation is just this, superscript negative, and that tells us that we're approaching from the left. All right, similarly, we can talk about approaching from the right. Here is an example of a function where the limit as x approaches a from the right is positive infinity, like so. And as if we're approaching from the right, we use a little superscript plus, right? So this means the limit as x approaches a from the right of f of x is plus or minus infinity, or it could be some number. All right. All right, now this actually lets us characterize a limit itself, the limit as you approach a point. This is why this is more of a definition, because it's another way of defining the limit at a point. And it basically says this: when we say the limit as x approaches a of f of x is infinity, we mean from both sides. We mean from both sides. We mean that the limit from the left is infinity and the limit from the right is infinity. So in this symbol, this is like a compact version of saying both of these. We like those kinds of shortcuts because we don't want to have to write everything out all the time, right? And then similarly, if we say the limit as x approaches a of f of x is negative infinity, we mean from both sides. We mean from the left side and from the right side. And if we need to specify that it's coming from the left or the right, we can. We can. So that's what it is. So when we talk about a limit as you approach a point, we mean from both sides, from both sides. All right. Okay. Now, why did we need to talk about this? What is the importance of this? Remember, always ask those big questions. Why do I care? Because this is how we're going to define vertical asymptotes. So now we're going to talk about vertical asymptotes and holes. And a vertical line is called a vertical asymptote of the function y equals f of x if it has an infinite limit from the left or the right or both. Okay? Infinite limit from the left or the right or both. And if that happens, you've got a vertical asymptote at that point. All right. So for example, maybe an easy example, the graph 1 over x. This is one of those important graphs that you should have memorized. The limit as x approaches 0 from the left is negative infinity, right there. And the limit as x approaches 0 from the right is positive infinity. There you go. So because even just one of those things happened, 0 is a vertical asymptote of the function 1 over x. Now, it doesn't have to happen from both sides. So if I go back to like this example here, this vertical line you see, that is an asymptote. Why is it an asymptote? A vertical asymptote. Why? Because the limit as we approach from the right is positive infinity. That's what defines a vertical asymptote, that limit behavior. And that's why we needed to have the limit operator involved. Here's an example, the other graph, right? 1 over x squared. As x approaches 0 from the left, f of x goes to plus infinity. So that means that 0 is a vertical asymptote of that graph. It also happens to approach infinity as x approaches 0 from the right. So that's a vertical asymptote, okay? All right, now that's all well and good. Now we have some like, I'll say, uh, definitions of these things, right? So, what is the difference between an asymptote and a hole, right? So, this is why we need some clarification, right? We need some clarification. So, let's say that you have a rational function that is not in lowest terms, meaning there's repeated factors in the numerator and denominator, okay? Like the numerator has the same factor as one in the denominator. Well, if x minus r is a factor of the denominator, but not a factor of the numerator, you will get a vertical asymptote. Okay, you will get a vertical asymptote. And the equation of that asymptote will be x equals r. That's it. Now, if x minus r is a factor of both the numerator and the denominator, you will have a hole. You will not have a vertical asymptote. You're just going to end up with something that's called a removable discontinuity. We're going to see an example in just a moment here. But essentially, if you've got x minus r in the top and x minus r in the bottom, then you're just going to have a hole at that point in the graph. You will not have that asymptotic behavior. You won't have that vertical limiting behavior. Um, there's a reason for that. So let me give you some intuition. So in the event that a hole or a discontinuity occurs, it's because a zero in the denominator is present, but the equivalent zero in the numerator is tamping down any infinite behavior that could occur. So think about it like this. As we approach a point, if there is an asymptote, then the values of the function are getting gigantic, right? They're growing and growing and growing. So it could be like this, it could be like this. It could be opposite sides like that. It could be like that. That's how you get a vertical asymptote. And that's what happens when you have a zero in the denominator. But if you have an equivalent zero in the numerator, then as the function tries to blow up, that equivalent zero in the numerator is beating it back down, right? Because even though the denominator is making it go like this, the numerator is going, hey, no, no, down, 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 down. That's what's happening. You're basically dividing the large amount by the large amount. And so that infinite behavior gets canceled out. And what you're left with is not infinite behavior, but you are left with a little hole right there. You're left with a hole because, again, the only reason that an asymptote would occur is if there's a zero in the denominator, which means that point is not included in the domain of the function. But that equivalent factor in the numerator cancels out that infinite behavior. That's the idea, all right? You're going to study these types of discontinuities more in Calculus 1, so we won't dwell on them a ton here. But the other thing is this, many times in practice, those holes are just kind of ignored. You're even going to see it in Mathematica in a few minutes here, because the value of the rational function at the hole can always be just defined to be the value of the reduced rational function at that point, filling in the hole. So it's one of those situations where there is a hole because of those repeated factors, right? But if you wanted to fill in the hole, you just say the output is going to be the output of the reduced function at that point. So a lot of times they just get ignored, but they are still there. So we can't pretend they don't exist. They do, but a lot of times people just brush them off. Okay, let's do an example here. Here's one where I want you to find the holes, the zeros, and the vertical asymptotes of this rational function. Okay, so think about it for a second. Let me throw the thinker up. All right. And now give your brain some verbal feedback. Maybe what do you want to try first? What are you going to do first? All right. And now try to work it out. You're looking for all of it, the holes, the zeros, the vertical asymptotes. Maybe I'll give you a little hint. Start by factoring. All right. Let's do this. Okay. So the hint is the biggest hint I can give you, factor everything. So start by factoring everything. Factor the numerator, factor the denominator. We know how to do that, right? We learned how to factor quadratics. We learned how to factor polynomials. Thankfully, these are just quadratics, so there's not too much work to be done. The numerator, excuse me, the numerator is a difference of squares. The denominator looks like it can be factored. Two numbers that multiply to negative 21 and add to 4. I see 7 and 3 in there. Positive 7, negative 3. I think that'll do it. Yep, that's it. Okay. So here is the factorization of r of x. And one thing I want to point out, or I'll say this, before we do anything else, once this factorization is done, write down the domain. First and foremost, write down the domain. X cannot be -7, x cannot be 3. First and foremost, okay? Now that we have written down the domain, notice that there is a common factor in the numerator and the denominator. That's where a whole is going to occur. So we're actually going to cancel those common factors. And then here we have written the rational function in lowest terms. Okay. So this reduced function, maybe you could call it R1, it is equal to the original function R of X at every single point except the whole that'll occur when X equals 3. So when x is 3, there will be a hole in the graph of r. But if we want to know exactly where that hole lies vertically, like on the graph, we just evaluate this reduced function at the number 3, and we get 3/5. That's it. So there will be a hole in the graph of r of x at 3, 3/5. All right, so we've got the holes now. Now let's do the zeros and the vertical asymptotes. Now that we've simplified everything, we've written this in lowest terms, now we can find the zeros and the vertical asymptotes. Here we go. The zeros are going to be the zeros of the numerator. So there's only one zero, and it's at x equals -3. And the asymptotes are going to be at the zeros of the denominator. There's only one, it's at x equals -7. Now we've got it, all right? Oh, and this has multiplicity 1, by the way. So that tells us that when x equals 3, the graph is going to cross the x-axis. It'll either look like that, or it might be a little more eccentric like that or that, okay? So let's take a look at the graph. Here it is. I'm gonna zoom in on the pieces here. For one, notice we have our vertical asymptote when x equals -7. So the graph is going like this on that side. It's that infinite behavior that makes it a vertical asymptote. Here is our one hole, I'm sorry, here's our one zero, and that zero occurred at -3. Sorry, it's a typo. That should say -3, not 3, just like that. And then there's a hole over here. There's a hole at 3, 3/5. And again, this is one of the reasons why those holes get ignored a lot of times, because how did we find the location of that hole? We just reduced the fraction to write it in lowest terms and then evaluated that function at that hole. And that gave us the location of the hole. But that's where it is, okay? So that's a rough sketch of the graph there. And what we're building up to that we're going to finalize in the next section is how to draw these graphs by hand, okay? That's what we're building up to. We're going to start by looking at local behavior now, then we're going to talk about global behavior in 3.9, and once we know about the local behavior and the global behavior, we can make sketches of these graphs by hand. Okay. Oh yeah. All right. So some other good news. Uh, the factors and the zeros in the denominator, they can be repeated. That's not uncommon. They can have a multiplicity, just like we saw before, by the associated exponent. Oops. Given by the associated exponent, just like we saw before. So if we're given a rational function in lowest terms, if the factor x minus r appears exactly m times in the denominator, then we say the multiplicity is m. So this is really, really similar to what we saw with polynomials, but now it's for asymptotes. So it's very, very similar, not too much different, not too much more to learn, right? Same thing with the zeros of a rational function. The multiplicity of the zeros of a polynomial tell us about the local behavior at the zeros. Well, guess what? The multiplicity of the zeros of the denominator tell us about the behavior of the vertical asymptotes of the graph, which is pretty cool. So here is the specific technical definition for this, or proposition for this. Let's say you've got r of x, it's a rational function in lowest terms. If the multiplicity of a zero in the denominator that gives rise to a vertical asymptote is odd, then the graph will approach plus infinity on one side and negative infinity on the other side of that asymptote. If the multiplicity of a zero in the denominator that gives rise to a vertical asymptote is even, then the graph will approach plus infinity on both sides, or it'll approach negative infinity on both sides. Sounds a little bit familiar, but here's the big idea. If the multiplicity of a zero in the denominator is odd, then the graph is going to look like 1 over x there, like that, or like that, like that, like that. That's it. So, so if the multiplicity is odd, then your graph will look like 1 over x at that asymptote. If the multiplicity of a zero is even, then the graph will look like 1 over x squared. It'll either look like this or it'll look like that. So that tells you everything you need to know about the asymptotes. If you look at the factors of the denominator and you see a multiplicity of 2 or an exponent of 8, you know that at that asymptote, the graph has got to look like x 1 over x squared or negative 1 over x squared. It's got to be one of those two. All right. That's the big idea. Pretty straightforward. So let's try this. We're going to draw a rough sketch of this rational function. Um, yeah, let's just try this. So this one's actually not too bad. One thing I noticed right away, the numerator is super simple. It's just 1, right? But the denominator is fully factored, so that saves us a lot of work. Thank you for that. Um, so we're going to have asymptotes at all these points. Yeah, there's no common factors in the numerator and the denominator. So let's start by doing a rough sketch here, or let's start by drawing the axes. Here we go. X, Y. Now let's plot our asymptotes. Looks like we're going to have an asymptote at -3, -2, 1, and 2. And I'm going to use my, there it is. There we go. So there's one here at -3. Maybe I'll sketch it like this. There's another one at -2. There's another one at 1. And there's another one at 2. Okay, there we go. Let me label these -3, -2, 1, and 2. Okay, now we want to know what the graph looks like around these asymptotes. And that is exactly where the multiplicities are going to come in. Let me highlight those. So this one is just 1, this one's 2, 3, and 4. All right. So what we can tell just by our intuition is that around this asymptote, -3, the graph's either going to look like this or it's going to look like that. I'm sorry, it's going to look like this or it's going to look like that. That's basically the idea. It's got to look like that, one of those two options. How do we tell which one? Well, let's look at the behavior on the left side of -3. Let's see if we can figure out if the graph is going to go to positive infinity over here or negative infinity over here. We just need to pick some number that is close and then plug it in and see what we get. So maybe I'll pick the number, I'll make it easy. Let's just pick like -4. Okay, so let's say x equals -4. Then down here, we're going to get -1. We're going to get -2 squared, -5 cubed, -6 to the fourth. Okay, so then we're going to have negative, positive, negative, positive. Is that right? Negative, positive, negative, positive. Okay, negative times a negative is a positive, positive times a positive is a positive, so it's positive. So we know the graph is going to look like this on this side. And then since the multiplicity of that is a 1, it's got to go like this at the bottom. That's it. Now, here's where it gets a little more interesting. This is kind of building up to what we're going to do in the next section. What does it look like around the asymptote x, I'm sorry, x equals -2? X equals -2. So here, the multiplicity is even. So it's either going to look like 1 over x squared or -1 over x squared. Now, is it going to look like this? Or is it going to look like this? That's the question, right? But notice that if this were to actually be up here, then the graph would have to pass through the x-axis. That would mean there's a zero in there. There's a zero, but this denominator has no zeros. No zeros whatsoever. So this can't be this. In fact, what's got to happen is the graph has to swoop up and then come back down like that. There it is. That's it. And then let's see what happens next. It's also got to come down like this, right? This looks like negative 1 over x squared. Okay, what's happening now? What's happening over here? Let's see. Well, let's see what goes on at x minus 1 or x equals 1. The multiplicity is 3. So, well, there's no zeros, so it can't cross, right? It's got to do this again. But because this multiplicity is odd, it's going to have to come up like this, just like that. And the idea is that right around this asymptote, it looks like that, or it looks like that. So everything's being determined by the fact that there are no zeros and the local behavior at those asymptotes. So we got 1. Now let's do 2. 2 is even, so it's got to swoop back up. Oops. Swoop back up like this again. And then it's got to swoop back up like this, again, because the multiplicity is even. So here, this is just a super duper rough sketch. But the idea is that all I had to do, and clear this, was look at the multiplicity of these asymptotes and then look at the zeros and tested like 1 point over here. And with that information, I could get a very rough sketch of what the graph looks like. We're going to get even more precise in the next section, but this is a good place to start. All right. Now, just to kind of finish things off, let's talk about some helpful Mathematica commands. Now we've seen what the local behavior looks like. We still have the issue of, dealing with all these polynomials. The numerator is a polynomial, the denominator is a polynomial. In order to find the local behavior, we need to factor these things. So we need to factor polynomials, and this is where Mathematica can come really in handy. So naturally, there's a bunch of Mathematica commands that can make our analysis a lot easier. We already saw the factor command, and it works on polynomials, but it also works on rational expressions. So if you put a rational expression into the factor command, Mathematica will factor the numerator and the denominator, right? But here's the catch. The catch is it'll automatically reduce the expression, meaning it'll cancel any common factors and it will eliminate the wholes, right? Kind of like I was saying earlier, how the wholes get kind of ignored. Mathematica kind of ignores them. It basically cancels everything for you and simplifies it. So that may or may not be helpful depending on our particular application. There's also the command numerator, which just picks out the numerator of a rational expression. There's the command denominator, which picks out the denominator of a rational expression. And then there's the command numerator denominator, numerator denominator, and that gives you a 2-item list containing the numerator and the denominator of a rational expression. But again, it will simplify it. It'll simplify it and cancel any common factors that are in there. Okay, let's take a look. We're going to use this as an example. um, Again, remember, these are the types of functions that you're more likely to encounter in your actual career. The functions are not going to be super nice with low degrees. The degrees can be really high. They can be really, really high degree polynomials. Think hundreds, thousands, millions, that kind of thing. So we want to have technology to help us. Let's pull this up in Mathematica and use some of those commands. Let me pull that up right here. There we go. Again, this is posted on Canvas, so if you want to follow along with the file on your own, you can. Or you can just kind of watch here and we'll show you what's going on. So here, I instantiated the function r of x just to make the analysis a little bit easier. I pretty much just copied and pasted or wrote it by hand, either way. Now I'm going to factor it. So look what happens when I use the factor command on the rational function. Boom, it's instant, right? It immediately factors it. One second here. Yeah, there we go. Yeah, it immediately factors it, so it doesn't take very long for it to do. But if there are any common factors, it will have already canceled them by the time this shows up. Next, there was the command numerator, and I actually instantiated it as another function just because to be extra, right? Or maybe it's efficient. It's not extra, it's efficient. So now if I ever want to refer to the numerator, I can just write num of x, right? But numerator will just pick out the numerator of this function. It won't do anything else. Wait, where'd you go? What? Hold on. Num of x equals, wait, what? Hang on a second. Oh, maybe I forgot to compile R of X, and so now it's gonna, huh, hold on one second. Okay, sorry about that. So, as usual, I'm just overlooking something obvious here. So here I'm defining the numerator, this num function to be the numerator. So when I compile it, it's just defining it as the numerator. If I wanted to actually list the numerator, I need to call that function. So I need to actually have it spit out the numerator. So there you go. Then it spits out the numerator. No changes here. It just spits out what the numerator is. But remember, Mathematica writes it in like reverse standard form. There you go. So then denominator, same thing like that. I'm going to have it run it, and it just picks out the denominator. The utility of these is straightforward. If you need to pick out the numerator and denominator, you can. And then same thing here. This one, notice I didn't actually define it as its own function. So here, this one should be fine. Yeah, and this will give you a list, a two-element list of the numerator and the denominator right here. And that's it. Again, Mathematica will automatically cancel any common factors. So this may end up being in reduced form. That's one of the maybe the downsides to using this command. And sometimes you really do want to pick these out separately if you want to look for things like holes. Uh, Another thing I wanted to throw in here is the roots function, right? We talked about the roots function in the last section. We can use that on R of X. So here I'm going to say, hey, Mathematica, what are the zeros of R of X up there? And I'm just going to use the roots command, and it spits them right out. Negative 1/3, 1/2, -4, -2, 1, and 3, just like so. You can also just read that off by looking at the numerator, just like so. Oh, you could also compose these functions. You can factor the numerator just by wrapping this in the factor command. A million things you can do, right? Um, Here, I actually have it finding the roots of the numerator like so. Notice that the roots list here is the same. This goes back to early on in the section, right? The zeros of a rational function are equivalent to the zeros of the numerator as long as that rational function is in lowest terms. And in this case, it is in lowest terms. There aren't going to be any common factors. We could even double check that. Let's add that on at the end. I want to factor num x. Oops. Okay, now I want to factor den x. Okay, are there any common factors in there? Let's look. Nope. No, close, but not. No, different signs, right? Okay, so there are no common factors in the numerator and denominator, which means R of X is already in lowest terms when it's written like this. So there are no holes and there's nothing to cancel. And that means that the roots of the numerator are going to be the zeros of the rational function, all of them. What about the denominator? Let's do the roots of the denominator. There we go. So these are going to be the equations of our asymptotes, vertical asymptotes. X equals -3, x equals 2, and x equals 7. So we've got the x-intercepts, we've got the asymptotes, we know there's no holes. We've almost got a complete picture of the function itself. There's only one thing that we're really missing, and that's the end behavior. We don't know what's going on at the end of these functions just yet. And that's what the next section is all about. All right, let me go back to the slides. I think that is just about it. Oh yes, this is just me plugging in, um, yeah, actually writing out what happens when you plug this stuff into Mathematica. There we go. Oh yeah, and we can see that the lists are the same. So here, the zeros are the same as what Mathematica gave us, which makes sense. All right. Yeah. Okay. Oh, this is also just kind of adding to what I said before. Mathematica will cancel any common factors. If we needed to see the whole, we could factor the numerator and denominator separately, which is what I did. If you end up with a lot of zeros and a lot of I'll just say zeros of the denominator and zeros of the numerator, you might have a really, really long list, right? But what you can do is you can just use the Mathematica command intersection to find if there are any common zeros, and then that'll let you know where the holes are. All right. Okay. On that note, let's play. I'm excited to work with you all on this one. This is another Mathematica activity. Again, it's good to just get some experience with these tools. You don't need to become a master at them. You just got to be aware that they are there and that you can use them. And there are a couple questions on the homework where you'll get to use them as well. All right. Okay. So we've only got one more section in this chapter. We're going to learn about the global behavior of rational functions in section 3.9. And on that note, thank you very much again, and I will see you next time. Happy studying.